Good morning, everyone. Today I'm honored to present our work, FlowGS, controlling information flow for graph-based interaction in 3D Gaussian splatting. I will start with introduction, covering our motivation, existing limitations, and core insights. 3D Gaussian splatting delivers real-time, high-quality writing with explicit anisotropic primitives and efficient retrogression, which is a landmark of neural writing. The crucial flaw lies in its independent optimization rule. Each Gaussian updates without modeling spatial links between nearby primitives. Without local structure priority, the algorithm clones and splits massive Gaussian to fill fault surface. As shown here, under reconstructed areas keep cloning, while float zones struct redundant primitives. Since easily contain millions of Gaussians, bring heavy memory and bandwidth costs that hinder large-scale deployments. We wonder, can we introduce neighborhood interaction to balance quality and compactness without oversmoothing and unstable optimizations? Many recent works build graphs on Gaussians, which we divide into 3 parts with shared defects. Graph augmented method, such as Gaussian, GraphJS, propagates features with fixed equal aggregation width. Next is compactness-oriented methods such as mini-splatting, compacted 3DJS, cut Gaussian neighbors but keep unchanged feature sharing logic. Next is optimization drive method such as MCJS. Adjust sampling without link each Gaussian to its neighbors. Or lake adaptive control over information injection intensity. Fixed with trigger to series defects in joint geometry appearance optimizations. First, edges and specular highlights fade after repeated neighbor averaging. Second, unchangeable widths break geometry color balance and cause training oscillation. Thus, we raise our core question. Can we redefine Gaussian neighborhood interaction as an information flow control problem to fix these issues? Now we introduce our core insights. Previous graph method merely transport features with fixed topology and equal width. Instead, we modeled neighborhood interaction as a completed information flow control system with 4 controllable dimensions: source, path, intensity, and update cadence. Topology: who connect to whom? Routing: which neighbors matter more? Intensity: how much self-neighbor feature to keep? And stabilization: how to avoid oversmoothing and guarantee convergence. Regulating the 4 dimensions systematically is FlowGS' foundation, enabling few Gaussians and better writing quality. We designed 4 method model corresponding to these 4 dimensions. First is dynamic KN topology. Adaptive native graph refreshed with Gaussian splatting and purine. Next is connected aware attention routing. Learning embeddings for selective neighborhood aggregation. And next is learnable dual gating. Two independent gates to adjust future fusion. And the last is delay activation and graph regulation. Lightweight rules to stabilize training. These models form an integration information toolkits, achieving our less is more performance gain. Next, we elaborate 8 models implementations. Let's go first through FlowGS or overall pipeline. Give row 3D Gaussians. The framework runs 3 depths. Dynamic graphic construction, attention aggregation, and dual gating fusion. This model builds adaptive information channels. Gaussians distribute unevenly. Dense on texture, sparse on plan. Fixed neighbors fail to fit varying density. For each Gaussian enter μi, we search nearest neighborhoods and refresh the graph every 100 iterations, or when Gaussian count changes. As the 3 diagram display, Kn auto adjusted refractive fields, such as sparse air, wider range to collective contents, medium density, balanced neighbor range, and dense texture. Fix on local fine details. This density adaptation captures geometry better and resists Gaussian drifts, laying a solid base on attention routing. Topology defines communication together, while routing filters valuable neighborhood information. Traditional uniform wise WIG average all neighborhood equally and creates over smoothing by absorb irrigant noise. We equip every Gaussian with latent vector HI, splitting into guide embedding GI for routing and gate code ZI for gating. We calculate dot product attention and softmax width to aggregate neighbor features. From the white heat map, matching neighborhoods gets high width will mismatch the one sub-surprised neighbor to 0. This anisotropic aggregation previous fine detail and outputs clean feature for dual gating. Routing decide information sources. Dual gating control absorb strength. Combination single gates result alpha plus beta equal 1. Enforce a trade-off between detail and context. We generate independent alpha beta will sigmoid layers without the sum construct. The 3 flexible working modes are unlocked. Detail preservation, large alpha, small beta for edges and highlights. Context filling, small alpha, large beta for smooth flat regions. And signal amplification, large alpha and beta for constant homogeneous areas. This decoupled design is the core reason why FlowGS retains sharp texture while reducing redundant Gaussians. The last stabilization model limited graph-induced gradient oscillation with 3 highlights with structures: timing control, frequency control, and weak graph regularization. Build a completed stable training envelope turning graph interaction into a reliable built-in component of 3D.js.
Now let's look at what FlowGS actually buys us. First, the quantitative picture, then efficiency, and finally the visual and ablation evidence. The key point of this table: both methods are trained under the same iteration budget, so it's a controlled comparison. Across all three benchmarks, the story is consistent: higher PSNR and substantially fewer Gaussians at the same time. Two honest flags. On MIP NERF 360, LPIPS goes slightly the wrong way, a mild compactness perception trade-off, which I will return to, and our 3D.js baseline is rerun by us under identical budget, so it's the strongest controlled comparison on the table. The others are cited from their papers. Fewer primitives isn't just a storage win. It shows up at runtime because rasterization cost scales with primitive count. Rendering throughput goes up on every benchmark and the parameter memory shrinks sharply. The one cost is training time and it's scene dependent. Modest overhead on some scenes, but on deep bleeding, we are actually faster because fewer primitives speed up densification. So the real message is representation efficiency, not a trivial rendering trick. These are the hard, high-frequency regions, like piano keys, ceiling lighting, vehicle logos. FlowGS keeps the fine structure while vanilla 3D.js blurs or distorts it. And I'd frame this as representative evidence that complements the matrix, not a substitute for them. But they line up with the numbers and they support our hypothesis. Controlled neighbor interaction preserves local structure. This slide is about why standard 3D Gaussian splatting spreads Gaussians almost uniformly to guarantee coverage. So many primitives are spent on flat, uninformative regions. FlowGS instead concentrates density on high-frequency structure and it thins out the most areas. That pattern corroborates our mechanism. Selective information sharing casts redundant allocation. The rigorous casual check comes from the ablation, which is next. One protocol notes that the numbers are confusing. The ablation averages a subset of things, so this figures differs slightly from the highline table. The graph module is the heart of the method. Removing it is by far the most destructive. Quality collapse and the primitive count blows back up. Oh, sorry. Attention routing. If we swap learned attention for uniform pooling, quality regress and reluctancy returns. So adaptive weighting is what's doing the work. Dual gating a single gate underperforms. Controlling self-preservation and neighbor injection independently is what helps. And to subtler findings without regularization, the model gets marginally fewer Gaussians, yet perceptual quality is worse, which makes our philosophy explicit. Compactness is not the standalone target. Fidelity comes first. Without delayed activation, results are near par, but with more primitives. Interaction is more robust when we switch it on after the geometry has settled. And regularization barely moves peak PSNR, but consistently improves perceptual quality and stability. So we present it honestly as a soft prior, not a May driver. Let me put this together. The core idea: reframe Gaussian interaction and control the information flow, broken into 4 complementary dimensions: topology, routine, intensity, and stability. In the architecture, that's a dynamic graph or topology, latent guided attention for data-dependent routing, and two independent gates balancing self versus neighbor information. The evidence spans many things across 3 standard benchmarks. Consistent quality gains with a large reduction in primitives, and we document that the one perceptual trade-off openly. Practically, the compact representation means faster inference and smaller storage. About the limitations, the method is stacked-in only, and the LP-IPS trade-off on MIP-NERF360 comes from weak local smoothing in distant and background regions. And our controlled baseline is rerun 3DGS while the other methods are cited. Going forward, we will extend the framework to dynamic 3DGS and analyze the learned gates and attention to see when the model favors detail versus smoothing, and build a unified, reproducible benchmark reporting variance across seeds. That's the end of our presentation. Thank you.
Thank you very much. Are there any questions? One question here.
Thanks. That was a very interesting presentation. So the result on the deep blending data set is very impressive, right? You get something like 6 dB increase in PSNR. I've never seen that before. So do you have any intuition about these scenes in particular? I mean, these scenes are hard, right? Peter Hedman took them when we were doing the paper at the time. And the pictures are very randomly placed in the scene. They're not very continuous. So it's a very hard capture. So why does your method work so well in particular for this capture? Do you know?
Our innovation is dynamic graph construction, attention aggregation, and dual gating fusion.
Why in particular for this capture compared to the other ones? Do you know why it works so well in the unstructured capture?
Sorry, we will learn after.
Any more questions? Then I have a question. So you're saying that you're generating the graph topology just based on the centers of the Gaussians, right?
Yeah.
Did you ever run into any trouble because you're not also considering the extent of the Gaussians? Because especially for like very large anisotropic Gaussians, the center might not actually be a good proxy for the neighborhood, right?
I have some more trouble in train the network, and when we add some components in this training, we found the LP-IPS trips, and but we found it's not trouble. It's just it choose of the training.
But that was that specific to considering only the centers instead of like the entire size of the Gaussians? All right, we can also talk about it afterwards. Any more questions? Then let's thank our speakers again.